Hi there, I'm Jeremy Krug, and in this video we're taking a look at Unit 4, Section 6 of AP Chemistry, which is all about titrations. Now, there are several types of titrations. The most common one that we're going to carry out in AP Chemistry normally is acid-base titration, but there are others. You can have oxidation-reduction reactions in a titration. You can have precipitation reactions in titration, complexometric titrations. But the basic idea is that you're going to have a setup that looks kind of like this. Now this long slender tube, this is called a burette, and you're going to normally place a base. It could be some other substance, but usually a base goes in that burette. And then in the Erlenmeyer flask down here, you're going to place the acid. This could be something else, but generally speaking, it'll be the base going in the burette and the acid going in the Erlenmeyer flask. And normally the way this works is you'll measure out a very specific amount of acid into that flask using a pipette or some other volumetric instrument, and then you'll place the base in this burette and you'll just start titrating. You'll open up this stopcock down here and allow as much base to flow into the flask until the reaction is complete. And the goal is, when the reaction is complete, you're going to have something called the equivalence point. Now at the equivalence point, the moles of acid in that flask will be exactly equal to the amount of base that has flowed into that flask as well. At that point, the reaction has achieved completion. And you basically have the, well, as we say, the equivalence point. Moles of acid equal moles of base. However, you probably are aware that most acids are colorless. They don't really look like anything. And the same is the case with the bases. They are colorless as well. So the question is, how are you going to know that you have reached that equivalence point, that point where the reaction is essentially complete as far as we're concerned? Well, you're going to have to put something into this acid in order to indicate that that's the case. And we put an acid-base indicator into the acid down here. Now, what that means is when you get to as close to the equivalence point as possible, you're going to see some sort of a color change. In a lot of cases, if it's an indicator called phenolphthalein, the colorless acid is going to change to a pink color in some cases. And that moment when the color changes is called the end point. Now, if you're doing your job right, the end point should be very, very close to the equivalence point. Now, they're not exactly the same thing, but they should be really close to each other if you're doing your job right. The end point is where your color change indicates that, yeah, this is where the reaction has essentially completed. Now, let's take a look at a couple of examples here, some chemical reactions that are acid-base reactions. And these reactions could be carried out using a titration if you wanted to. In the first example, we have a few drops of concentrated hydrochloric acid that are added to a solution of sodium fluoride. So once again, we're going to use the same rules as we did for writing net ionic equations back in Section 2 of this unit. So we'll start with the hydrochloric acid. We know that that is a strong acid, and so you have to write that in its ionized form. So we're going to write it as H plus and Cl negative, since strong acids are completely ionized. And then we have sodium fluoride. Well, that is a very soluble compound. It starts with sodium, so we can write sodium fluoride in its ionized form as well. Completely soluble, so it's Na plus and then F negative. And just like we did for all those other net ionic equations back in Section 2, the ions are going to try to swap partners. And it's our job to try to determine which one of these pairs is actually going to make something in the reaction. Well, we might remember back to our solubility rules. We know that sodium chloride is a very soluble ionic compound. So that's going to remain in ionic form. However, H plus and F negative, well, that creates hydrofluoric acid, which is a weak acid. Now, it's not so much that hydrofluoric acid is insoluble as it is a non-ionized compound. And so we want to think of it in that term. We're going to take those and put them together to make a weak acid. That means that sodium and chloride, of course, are the spectator ions, and the H plus and F negative will combine in their aqueous forms there to make hydrofluoric acid, which is also aqueous. So anytime you're creating a weak acid like that, it's going to be in the non-ionized form. Let's try another example of an acid-base reaction. Dilute sodium hydroxide is titrated into a flask of 0.10 molar hydrochloric acid. So once again, we have a strong base, which is the case for sodium hydroxide. That means it's going to be completely ionized, right? Strong acids and strong bases are completely ionized, and that's the case with hydrochloric acid as well. We write that as H plus and Cl negative. And once again, just like in the last example, these ions are going to try to swap partners. We know that Na plus and Cl negative are spectator ions because that would just make a very soluble compound again. So that's not going to work. So H plus and OH negative, that's the pair that's going to get together. So we're going to make, you can probably figure it out, it's just water out of this. And that means that sodium and chloride are our spectator ions. So our net ionic equation will be H plus aqueous plus OH negative aqueous yields water in its liquid form. Now, just a little shortcut here, you'll actually notice that this is going to be the net ionic equation anytime you combine a strong acid with a strong base. So if you can take a look at an acid-base reaction and recognize that you're adding a strong acid to a strong base, you can just skip right ahead and write down H plus OH negative yields water as the net ionic equation. I hope you learned something about acid-base reactions. We're going to talk a little bit more about this here in an upcoming section. If you learned something, please smash that like button and join me in my next video in which we're going to talk about oxidation reduction reactions in Unit 4, Section 7. Thanks for watching.